So in the previous lesson we looked at perpendicular vectors in 2 dimensions. This time we're going to look at 3D perpendicular vectors. And so the goal again here is we want to find a rule to prove that 2 vectors that are 3D are indeed perpendicular, or if we know they're perpendicular, what can we say about them? So it's very similar to what we talked about with the 2D vectors. In fact, the drawing is going to be very similar as well. We're going to have 2 vectors. We'll have this one, we'll try to color code them again. So we'll have a red vector and a blue vector, and we'll say that they are perpendicular. And we'll call the blue one B, the red one A, and then we'll have the hypotenuse vector, which will be, we'll call this point B and A again, so this will be vector BA. So, the components of vector A are A1, A2, A3, and then the components of B are likewise going to be B1, B2, B3. And so that means that vector BA here, this green vector, well, we'll come back to that in just a second here, but we want to find the magnitude of A, B, and the green vector. So the magnitude of A is the length of A, and the way we do that is just like we do in 2 dimensions. We use the distance formula or the Pythagorean Theorem, however you want to look at it. It's A1 squared plus A2 squared, why did I write a B there, plus A2 squared plus A3 squared. Take the square root of all that. And the magnitude of vector B is going to be very similar. We're going to do B1 squared plus B2 squared plus B3 squared. And then we're going to look at the hypotenuse, this green vector here, and we want to find the magnitude of that vector. And so, very similar to in 2 dimensions, the magnitude of BA, we're going to find the x distance, which will be A1 minus B1. And we're going to square that. Then we'll find the measure of the y distance, which will be A2 minus B2. I'm going to square that. And then we'll find the measure of the z distance, which will be A3 minus B3. And we'll square that. So this is the distance of the hypotenuse vector, the magnitude of that hypotenuse vector. And so what I'm going to say here is these 2 original vectors, A and B, are perpendicular. We're going to, just like we did with 2D vectors. And we want to use the Pythagorean theorem to find out something, like the last time we looked at the dot product, what's going to happen this time? So let's take a peek at that. We're going to have to shrink this, give ourselves a little bit of room here to work. So I'm going to move this up here, and we'll move it over on the right hand side. And so I'm going to do the Pythagorean theorem. It's going to be A1 squared plus A2 squared plus A3 squared. The square root of all that squared. So this is our beginning of the Pythagorean theorem. Plus this other stuff, the square root of B1 squared plus B2 squared plus B3 squared. Excuse me for the messiness there. Here, I'll clean that up a little bit. Not much better. And that's going to equal, I'm going to run out of room here, so I'll write it on the bottom. So it's A squared plus B squared equals C squared. So our C squared is going to be this stuff. A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 squared. So we've got our, and then all of that squared. We've got our Pythagorean Theorem. Looks like I forgot a squared on this blue guy here. A squared plus b squared equals c squared. And then when we square the square roots, they end up canceling out. So just like we had on our 2D vector, we have a1 squared plus a2 squared plus a3 squared plus b1 squared plus b2 squared plus b3 squared equals this green stuff, a1 minus b1 squared plus a2 minus b2 squared plus a3 minus b3 squared. So let's take a peek at this right hand side. We have three things we have to FOIL out. So I'm just going to look at this right now. We're going to take a little kind of sidebar here. I don't like that. We'll just kind of do a little dash. So when we FOIL the first part, we get a1 squared minus 2a1b1 plus b1 squared. When we FOIL the second part, we get a2 squared minus 2a2b2 plus b2 squared. And then when we FOIL the third part, we get plus a3 squared minus 2a3b3 plus b3 squared. So this green stuff is all the right-hand side. So what's going to happen is, much like we did with 2D vectors, we're going to subtract stuff on both sides that are going to cancel out. So I'm going to subtract a1 squared from both sides. I'm going to subtract b1 squared from both sides. I'm going to subtract a2 squared, that's supposed to be squared, from both sides. I'm going to subtract b2 squared from both sides. I'm going to subtract a3 squared from both sides. Probably get the idea. a3 squared. And subtract b3 squared from both sides. So all these things end up canceling out on the left side. We're left with 0 again. And 0 equals negative 2a1 b1 minus 2a2 b2 minus 2a3 b3. And like we saw with 2D vectors, we divide everything by negative 2, and we get 0 equals a1 b1 plus a2 b2 plus a3 b3. And so this is very, very similar to what we saw with 2D vectors. It's kind of the same procedure, and this part right here, once again, is called the dot product. This is the 3D dot product. Or inner product, if you prefer that terminology. 3D, I want to make sure that's a little bit more legible. So it's the 3D dot product. So what that tells me is if I take the x coordinates of the two vectors and multiply them together, and add the y coordinates of the two vectors and add them together, and then the z coordinates, multiply them together and add to the x and y, and if all these cancel out to 0, then the two vectors have to be perpendicular. So we can do the same thing that we did in 2D that we do in 3D to find if two vectors are perpendicular. So whenever a question comes up, are these two vectors perpendicular, the best way to test it is just plug it into this dot product. If the dot product is 0, then you know the vectors are perpendicular.